Okay, let's just motor through this review here from last time. So what is an angle? It's two rays with the same endpoint called the vertex. And we said the attribute, what is the attribute of the angle that we're assigning a value to when we talk about measuring an angle? What attribute are we talking about? Yep, someone said the openness, right? So it's how open the rays are, right? And which of these three has the greatest openness?
B.
Does B have the greatest openness? Yeah, so it's the most open, right? The most open. So therefore, if we're choosing some kind of convention to measure these angles, B is going to end up with the greatest value of the greatest angle measure. C will have the least measure. Okay, and then we did the design the pizza cutter, and the result of that was to realize that what is angle based on. So the whole point of this was to see what angle is based upon. And what did we conclude about the basis for measuring angles? Remember? Yeah, really, it depends on a circle, right? And so it depends on arc length, or specifically, like, portion of arc length. So one way to think of it is percent or fraction of a full circular rotation. Or arc length relative to circumference. So again, it's two different ways of saying the same thing. So arc length relative to circumference, well, that's the fraction of the whole circumference that is the arc length. Okay, so here's just a little. So in light of that, if it's based on percentage or fraction of a circular rotation, then how would we measure that angle? Well, we'd put its vertex in the circle, and what would we call that angle right there? What would we measure that angle?
90 degrees.
90, what's 90? 90% of the circle? Is that what that is? 90% of the circle?
1/4 of the circle.
1/4, 25%. Okay? Okay, for this one, what percent or fraction of the circle, or like 2/3, right? 2/3 or 67%. Okay, how about this last one? What percent or fraction of the circle? 1/6. 1/6. So no matter which convention we choose to measure the angle in, it always boils down to this: what fraction or percent of the circle. And so they use this word in the book, so that the rays of the angle, they call it subtend. Subtend means to cut off. So the rays of the angle cut off an arc length, in this case, of 1/6 of the circumference. See that? So subtend means so the rays subtend an arc length. The rays subtend some fraction of the circumference. So just to make you aware that the book uses that in the worksheets in the homework. So it's subtend is a verb, and it means to cut off. So the rays subtend an arc length. Okay, so in light of this way of thinking about angle measure, then what does an angle of 1 degree represent? What's an angle of 1 degree? Yeah. Okay, 1/360th. That's the right idea. Can we say more about that? What's that? Well, subtend is a verb. Subtend means to cut off. So yeah, so we're going to kind of put that together. So the angle of 1 degree does what? Subtends 1/360th of the circle. That's right. Okay, so here this is like 1 degree. So here's a close-up of it. So what is that right there? If this angle is 1 degree, tell me about that arc length right there. 1/360th of the circumference. That's what a 1 degree angle is. It's the angle whose rays subtend or cut off an arc length of 1/360th of the circumference. So here's that written out. So whose vertex, so we place the vertex at the center, has rays that subtend an arc length, that's 1/360th of the circumference. Again, subtend means to cut out a piece. Okay, so what would an angle of 36 degrees? Angle of 36 degrees, how would you describe an angle of 36 degrees? So talk to the person next to you. How would you describe what an angle of 36 degrees is? So half the room should be talking right now. Find someone to talk to. So what would 36 degrees, I think that's a little too big. How would you describe exactly what 36 degrees is?
An angle with a measure of 36 degrees, the vertex is placed at the center circle, has rays that subtend an arc length that is 1/10 of the circumference of the circle.
So 36 degrees then would cut off from there to there would be how much of the circumference? 1/10. That's what a 36 degree angle would be. Make sense? Hold on a second here. Do those show up? Can you see those circles on there? Can you see them in the back? Can you see the circles? Okay. All right, so we're going to talk about a different. So degrees is one particular way to assign a number to the openness of an angle. Okay, so we know what 1 degree is. It's 1. It will cut off 1/360th of a full circle. All right, so we want to talk about a different way that we can use to measure angles. So I've got 3 circles here. See that purple bar there? What am I showing there by that purple bar? What radius? Radius of the small circle. And what is the radius of the small circle? 1. Okay. And what I'm going to do is I'm going to peel that radius off and maintain its length, and peel it off and lay it on its circle. Did you see that? Let me do it again. See it again. All right, so I'm going to peel it off the radius, but keep its length intact and wrap it on the circle. So what's the length of it now? Still 1. Okay, still 1. All right, what am I showing you here?
Radius of the second circle.
Radius of the second circle, which is what?
4.
4. Okay, I'm going to peel it off again, take it off its radius, and peel it off and lay it right there on its associated circle. What am I showing you here? Which is? 6. One more time. I'm going to maintain its length and wrap it on its circle. Okay, so I want you to with the person next to you, talk about 2 things that are different about these 3 arcs. The red, the blue, and the purple. 3 things that are 2 things that are different, and 2 things that are the same about those 3 arcs. Go. Two things that are different, 2 things that are the same.
I guess they all do same. The hard one is yeah, because it's all the same.
Okay, let's do different first. What's one thing that's different about these 3 arcs? Their length. The red one, how long is it? 6 units. 4 units and 1 unit. So they have different, those arcs have different lengths. Is there anything else that's different? That's the main thing, okay? That's the main thing. All right, what about the same? So what's the same about those 3 arc lengths? What's that? Are they marking off the same fraction of the circle? Yeah, so but it's the same fraction of its respective circle. Okay, good. What else is the same? Yeah.
If you take the ends of the radius and draw them to the center, it makes the same angle.
Okay. Yeah, and so that goes along with that. If it's the same fraction of a circle, then they're all going to mark off the same angle. So let's do that. Okay, and this is our convention when we're creating these circles or creating these angles from circles. The initial side or the initial ray is the positive x-axis. And it's often referred to as like the 3 o'clock position. Right? Because on a clock, that would be pointing right at that ray would be pointing right at 3. So they use this terminology a lot, the 3 o'clock position. And then the angle, the convention is that we start at the 3 o'clock position and we sweep counterclockwise. So the angles will often be, starting at the 3 o'clock position, sweeping counterclockwise. That's going to be the way that we normally do things. Okay, and so if we sweep this angle counterclockwise up to the end of these arcs, since they all give the same fraction of the circle, their respective circle, it's the same angle. Okay, what else is the same about those 3? Something else really important that's the same about those 3. There's something the same about the length of all 3 of those. Okay, this goes back to the same fraction of the circle. Right. So how, in terms of the radius, how long is that? 1. And how many radius lengths is that? 1. They're all 1 radius length. Do you see? Okay?
We say the length of the rays are proportional to each other
The length of the rays. What do you mean?
because at a unit circle of 1, the length of the ray itself is going to be proportional to the length of the ray at 4.
Oh, you're
Only
saying
4 times as big. As
you're
the
saying
length.
like the ratio of that to that
Yeah.
would be the same as that to that? Yeah, true. That's true. And it would be the same. Yeah. Okay, so this angle, what is it? It's the angle that subtends what? 1 radius length. Does it matter what circle? What about a circle radius 10? Same thing. It doesn't matter what circle you pick. That angle will always subtend an arc length of 1 radius length for its respective circle. Okay? So because it subtends 1 radius length, we call this angle 1, anybody know? Radian. That's what a radian is. Is the angle that subtends 1 radius length. So the number of radians is the same as the number of radius lengths subtended. So if I tell you that this is 1 radius length from here to here, and then also from here to here is 1 radius length. So from there to there is 1 radius length, and then from that tick mark to the end of our angle is 1 radius length. Then what angle am I? This is 2 radians. Okay, this is 2 radians because it subtends 2 radius lengths. What about the red circle? How many radius lengths is the red circle? 2. What's the arc length? What's the red arc length? 12, right? So it's the radius is 6, and we're going 2 radius lengths, therefore the total arc length is 12. Okay? So again, this is 1 radius length, and then I'm going to go further, another radius length, and then one more time. So what I want you to do is I'm going to want you to build a table. So we got the purple, and we got blue, and we got red. So for each color arc, you're going to make a table here. You're going to write out what the radius is, what the angle theta is, and S is our notation for the total arc length. For this particular scenario right here, where I said on the purple one here, that's 1 radius length, then another radius length, and then another. Okay? So, is the task clear? Do you know what you're doing? So you're making that table of 9 values for the purple, for the blue, and the red arc. For each of them, you're writing down what the radius is, what the angle is, and what the total arc length is. Go. Does it make sense?
I'm just thinking about the theta. How do we...
Oh, sorry, I didn't tell you. So radian, so radian is the angle measure. Okay, the conventional symbol for angle measure is theta. It doesn't have to be radian. Okay, so it doesn't have to be radian, but it's theta is our standard symbol for angle measure. In this case, we're dealing with radians. So this is radius, this is angle measure, and this is total arc length. Are we good now?
So our answer for theta is going to be in radians.
Yes, we're dealing with radians. Yep, we're dealing with radians. And this is this chart is for this scenario that I'm showing you here. Okay, so check or compare with someone near you if you think you've got it done. Okay, so for the purple, radius, 1, angle, 3, is it 3? 3 radians, total arc length, 3. Okay, blue, radius, angle, 3, arc length. Red. Angle. Arc length. She said 18. Agree with that? Does it make sense? Does that make sense? Okay, so what is the relationship between R, theta, and S? What is the relationship between R, theta, and S? Looking at this table. So R is how long your radius is. Theta is the angle, which is the same as number of radius lengths, right? So the number of radius lengths subtended is the same as the measure of the angle. And S is our total arc length. So what's the relationship between those three quantities?
R theta equals S.
He wants R theta equals S. The total arc length would be how long the radius is times how many radius lengths. Does it make sense? Should make sense. So I told you here there were three. So for this particular example, you mean? Yeah, I told you that this was 1, and then 2, and then 3. What's that? Yeah, so because it's the same angle then, this will also be 3 radius lengths, and this also will be 3 radius lengths. Yeah, because the number of radius lengths will cut off the same fraction of the circle no matter which circle you're talking about. So theta is angle measure, okay? But it has the same value as what? So theta is a measure of openness. It's a measure of the angle. But how do we get its value? How do we get that number? How is it that we're getting this number 3?
Total arc length divided by radius.
Radius lengths, right? Radius lengths. So that value, so really the theta is referring to an angle measure. But we get that angle measure from number of radius lengths. Which of those two, angle or radius lengths, helps us to make sense of this formula? That the total arc length is the radius times theta. So,
Number of radius lengths.
yeah, this should make total sense. If this is number of radius lengths, so we got a number of radius lengths times how long each radius is, that's going to give us the total distance along the arc, right? So it's like, how much is each radius? How many of them do we have? That's going to give us how far we go along the arc. So I'm just pointing out that although theta is angle measure, it really helps to conceptualize it in this formula as a number of radius lengths. Okay, any questions? Really important. Any questions on this? Okay, so I'm going to zoom in on just this purple circle here. So I'm marking off every time we get to the end of a radius length. So what angle would be this right here? So starting at the 3 o'clock position, sweeping counterclockwise to here, what angle would we be talking about? So what would it be right to there? For what? Radians, right? The openness from here to there would be 4 radians because it's the angle that subtends 4 radius lengths. Okay? What about right here? Almost all the way, but stopping right there. 6 radians. Okay? So to get all the way around, it's a little bit more than 6 radians. Okay, it's a little bit more than 6 radians. We'll talk about that in a second. Okay, so this circle is called the unit circle. It has radius of 1. Okay, so this is 1 here. How can this circle be thought to represent any circle? A circle of radius 1. How can it be thought of as representing any circle in the universe? Okay, because but you're still talking about different circles. So suppose go ahead. Something going to say? Go ahead. Go ahead. All right, anyway, so what if the radius was 60 meters? How can a circle of radius 60 meters be thought of as a circle, as this circle?
The ratio of the circumference to the radius.
What could the 1 represent? What's that?
Radius?
Yeah, so 1 would be just 1 radius length, right? And in this case, what is 1 radius length? 60 meters, but we could call it 1. And so then what would 0.4 represent? Right here, 0.4. Four-tenths of whatever the radius is. In this case, if it's 60 meters, then right there would be 4/10 of 60 meters. Okay? Or the circle could be, 0.4 inches. Really small circle. But we could still call the radius 1 because it would stand for 1 radius length. One of those would be the radius length. And 0.8 would be 0.8 of the radius. Okay, so the unit circle is kind of a really powerful idea because it could represent any circle, and that value 1, that radius of 1, then is just representing 1 radius length, whatever it is. Okay, whatever it is, whether it's 100 miles or half a meter or whatever it is. Okay, so suppose the circle has a radius of 20 feet. How long is that arc length right there? How long is the purple arc length if this has a radius of 20 feet?
80 feet.
80 feet, because? 4 radius lengths. Okay? Okay, so just for practice.
So without those little tick marks, we wouldn't now.
Yeah, I'd have to mark off. I'm marking off where each radius length ends.
Okay.
Yep. So just practice quickly identifying where you would end up on the circle for these angles. Where would the terminal side cut through the circle for each of these? 2.5 radians, 0.3 radians, 4.25 radians, 6.1 radians. And then -1 and -5. So get a partner and do these. Talk through them together. Just like you just get 1 minute where each of these would be.
You always work counterclockwise from the 3 o'clock position?
Normally, yeah, yeah. Okay, that's the first one. That's 2.5. Okay, 0.3, where will that be? There's 0.3. 4.25. That's the closest I can get. 4.25 is something like that. 6.1. That's 6.1. Okay, what about -1? What would that refer to? -1 radians.
All the way back to the
Working clockwise.
Clockwise. So how could we know how could we know how far to go here?
The same distance the other way around is flipped.
Yeah, there'd be some symmetry to it, right? So I could just drop the vertical line right through here. So this angle right here would be like -1 radian, because it'd be clockwise. Okay, so what about the positions of these whole number radians? Are they in symmetric places on the circle? They just kind of land in asymmetric places. So what would be really nice would be to know, say, how many radius lengths or how many radians to get us exactly halfway around, and then we could find angles for nice symmetric places on the circle. Okay, so let's do that. Let's just make a guess here. So for halfway around, how many radians to here? That's 3, and this one here? 4. Okay, so just make a guess. Initial guess here. 3.3, I heard. 3.3. That's 3.3. Too big or too small? All right, what do you want to try now? 3.2. Too big or too small? 3.1. Too small. So 3.1 is too small. 3.2 is too big. So how about halfway between? A little bit too big. 3.14. Is that it?
Just barely.
looks like
Too big or too small?
Too small.
Yeah, can you see it? It's a little bit too small. What gets us exactly half around the circle? Some of you are figuring this out. Okay, pi. This is the meaning of pi. You maybe have never known this before. But so what is pi? So 3 point. So if I can just put pi in here, and now it's right on the. So now you know what pi is. What is pi? How would you explain to someone who didn't know what is the value of pi? What does it mean? What's that? Okay, it has to do with half the circumference of a circle. It has to do with that, but what is that number pi?
It's the constant.
That's just something you knew before, right? So what are we saying pi is here?
Number of arc lengths to get held halfway around the circle.
Yes, it's number of radius lengths, right? So it's the number of radius lengths. It's a little more. Here's 3 radius lengths. How do we get exactly halfway around? It's this number 3.14159 radius lengths to get halfway around the circle. But if we stop there, 3.14159, we still won't quite make it halfway around. You have to keep adding these decimal values on forever to get exactly halfway around the circle. So we use the symbol pi to mean exactly the number of radius lengths or the number of radians that would subtend exactly half of the circle. So therefore, all the way around the circle would be 2 pi radians, and that's approximately equal to 6.28. So looking at our picture, does that feel correct? About 6.3 radius lengths to get all the way around the circle. All right, exactly, it's 2 pi. Okay, so this was kind of our introduction to radians, but we said that all angle measure is based on percent of the circle. So what percent of the circle is 1 radian? So let's return back to our starting point. What percent of the circle is 1 radian? Okay, someone's offered up. What did you offer up?
1 over 2.
He wants 1 over 2 pi. Is that right? Is that the percent of the circle? He's agreeing.
How'd you get that?
How'd I get that? Or how'd you get that?
Well, if the whole thing is 2 pi or 6.28, do 1 part of that.
So we want 1 radius length divided by
It's the ratio of what you have to the whole thing.
the whole thing. And both are radius lengths, right? 1 radian would be 1 radius length. All the way around would be 2 pi radius lengths. And I think you get 0.159. Okay? How many degrees then is 1 radian? How would you find how many degrees 1 radian is? Yeah, it's going to be the same percent of what for degrees? 360. So how do we take that percent of 360? What do we do? Multiply 0.159 times 360, 57.2 degrees. Okay, so here's the beauty of thinking of angles as percent of the circle. You never have to memorize a formula. All you have to know is what in any given convention that you're using, what a full circle is. So what's a full circle in radians? 2 pi. That's our full circle in radians. What's a full circle in degrees? 360. So that's all you need to know, and then you just need to understand how to calculate percent. All right, so let's do, how about 203 degrees. So we want to convert that to radians. What are we going to do first? And what will that give us? Why would you divide by 360? She wants to divide by 360. Is that a good choice?
Yeah, it'll give you the ratio.
Okay. It gives us percent of the circle, right? So what is that? Let's get that percent of the circle. 0.563. Okay, and so then how would we get radians from that? Yeah, so we want that same percent of a full circle of radians, which is 2 pi. So we take 0.563 times 2 pi. Tell me.
1.13.
No, that's not right. Times 2 pi. 0.563 times 2 pi. What do we got? 0.563 times 3.53. So what does that number mean? 3.5, actually 4. Yep, it's how many radians it corresponds to? 203 degrees. So the openness of 203 degrees is the same as the openness of 3.54 radians. Okay, so why this is really a good way to think about it is then there's other ways of measuring angles. Gradients. Say we want to go from gradients to degrees. So you just need to know one thing. What do you need to know? How many gradients in a full circle? And there are 400. Okay, so let's do 17 gradients. So this is a measure of 17 gradients. I want you to find how many degrees it corresponds to 17 gradients. Go. And then we'll do our quiz. How many degrees is 17 gradients? And radians for that matter too. What will be first? Percent of the circle. What, did you get the percent of the circle yet? 0.425. How will we get degrees from that percent of the circle? Take that same percent of 360. What is 0.0425 of 360? Tell me again. 15.3 degrees? Okay, what about radians? How would we get the number of radians that 17 gradients is?
Multiply by 2 pi.
What's it? We want the same percentage now. Instead of 360, we want the percentage of 2 pi. So 0.0425 times 2 pi is 0.267. So a little over a quarter of a radian is the same as 15.3 degrees, is the same as 17 grads, which all of them are 4.25% of a circle. A gradient is just another way of measuring angles such that there's 400 makes a full circle. Just another, it's just like degrees, but instead of 360, it's 400 to get all the way around. Sure.